Hi from Tokyo, Japan, and welcome to Jeremy's IT Lab. This video is about route selection, how routers build their routing tables and forward packets. Route selection is probably one of the most important CCNA topics, if not the most important, and that applies to the CCNP too. In this video, we'll review what you learned about route selection in the CCNA and build a bit upon that foundation, covering some extra details to deepen your understanding. Let's get started. To start, let's define route selection, because it's not one single thing. The term route selection is used to describe two different concepts. First, we have route selection in the control plane, how the router builds its routing table. A router can learn routes from various sources, like manually configured static routes or dynamic routing protocols. But which route should the router install in its routing table? It will install the best route or routes for each destination prefix. And we'll look at what best means in this context a bit later. Here's a quick example of route selection in the control plane. R1 has learned a few routes from different sources. A static route to 10.0.0.0/8, an OSPF route to 10.1/16, and an EIGRP route to the same prefix. So 3 routes to 2 different prefixes. Using the AD and metric values of each route, the router selects the best route to each and adds them to its routing table. That is route selection in the control plane, taking routes from various sources and selecting routes for the routing table. But there is also route selection in the data plane, the process of forwarding packets. We already covered this concept in the Layer 3 forwarding video at the beginning of the course, but let's review it in this video and compare it to control plane route selection. The question here is, which route in the routing table should be used to forward a particular packet? And the answer is the most specific matching route. Let's say a packet arrives on one of this router's interfaces, destined for 10.1.57.10. It matches both of these routes in the routing table. The IP is included in both the 10/8 prefix and the 10.1/16 prefix. So the router selects the most specific route, the matching route with the longest prefix, and forwards the packet along that route. And that's route selection in the data plane. Let's look at each type of route selection in more detail, starting with control plane route selection via AD and metric. First, AD. Routers learn routes from various sources. For example, connected networks, static routes, IPv6's neighbor discovery protocol, and dynamic routing protocols. And sometimes, multiple routing protocols run on the same router. Let's look at an example. We have 2 separate networks, one running EIGRP and one running OSPF. Both are connected to an ISP. In a simple setup like this, with one connection to the ISP, you could just use a default static route. But for this example, let's say they use BGP to learn routes to the internet. Then the 2 organizations merge and connect their networks. To exchange routing information with each other, they run both OSPF and EIGRP on this connection. They might use iBGP here too. So in addition to their connected routes and any static routes, these routers learn routes from multiple routing protocols. If multiple routes to the same prefix are learned from different sources, routers need a way to select the best route. And they use administrative distance, AD, for this purpose. AD is a measure of the preferability of the route source, and a source with a lower AD is preferred. Here's a chart with the default AD values for various route sources in Cisco IOS. Notice the AD of 255 for unknown routes. A route with AD 255 is treated as unusable and will not be installed in the routing table. Basically, it means the router doesn't trust the source. Hopefully, you already know most of these default AD values from your CCNA studies, but if not, I recommend memorizing them. At this point, you might not understand the difference between, for example, eBGP, iBGP, and local BGP routes, or internal and external EIGRP routes. That's fine. Just use the flashcards to learn these values, and we'll cover the different route types later in the course. In the CCNA, you learn the most common AD values, but you might not know that you can change them. You can modify the AD values of many route sources. You already know how to do that for static routes, configuring floating static routes by adding the AD to the end of the command like this. It works in both IPv4 and IPv6. Now let's look at the dynamic routing protocols. For RIP, you can use the distance command in router config mode. For OSPF, you can do the same. or you can use distance OSPF, followed by a keyword and the AD value. It lets you specify different AD values for inter-area, intra-area, and external routes. You can configure them all in one long command, or in separate commands like distance OSPF intra-area 90, then distance OSPF inter-area 100, etc. We'll cover those route types in the OSPF section of the course. For EIGRP, the command is distance EIGRP, followed by the internal route AD and external route AD values. We won't cover ISIS in this course, but it uses the generic distance command to set the AD. And then for BGP, you use distance BGP, followed by the eBGP AD, the iBGP AD, and then the AD for BGP local routes. Once again, we'll look at what these mean in the BGP section of the course. These examples show the IPv4 versions of these commands. The IPv6 processes use the same distance commands, but you have to enter them in the correct IPv6 routing configuration mode, which we'll see later in the course. Finally, you can also change the AD of default routes learned through DHCP in interface config mode. The command is IP DHCP client default router distance, followed by the AD. You usually don't need to modify the default AD values, but there are definitely use cases where you would want to make one routing protocol preferred over another. For example, you can make OSPF routes preferred over EIGRP routes by lowering OSPF's AD. Let's look at a scenario you probably won't encounter and observe how iOS behaves: tied ADs. This network uses both OSPF and EIGRP. So R1 learns about the 4.4.4.0 network connected to R4 through both protocols. Of course, EIGRP is preferred by default due to its lower AD. But what happens if I modify OSPF's AD to match EIGRP? Well, with matching ADs, the EIGRP route is still preferred. It's still in the routing table. I shut down the EIGRP process running on R1, and the OSPF route took over and entered the routing table. Now, what do you think will happen after I re-enable EIGRP with no shutdown? The EIGRP route returns to the routing table, winning out once again over the OSPF route. So it seems EIGRP routes are preferred, even with a tied AD. Let's look at another example, this time with OSPF and RIP. I currently have OSPF disabled. Only RIP is running on R1. First, I modify RIP's AD to match OSPF's. Here's the route in the routing table with an AD of 110. Next, I re-enabled OSPF. What do you think happens next? If you're like me, you'd probably expect the OSPF route to be used. Nope, the RIP route remains in the table. Let's disable RIP by shutting down R1's G2 interface. Of course, this causes the OSPF route to enter the routing table. Finally, I re-enabled the RIP interface and waited a bit for R1 and R3 to exchange their routing updates. But the OSPF route remains in the table. As you can see, the behavior here is a bit different from the previous example with OSPF and EIGRP. Let's do one more short example with static routes and EIGRP. R1 is running EIGRP on its G2 interface only, so it learns a route to 4.4.4.0 via R3. This time, I configured a static route with the same AD as EIGRP. Let's see what happens. The static route is preferred over the EIGRP route. So if routes from different sources are configured with the same AD, an internal algorithm decides which one is preferred. Some sources online say the default AD is used as a tiebreaker, but that's not always the case. The OSPF and RIP example demonstrated that. Even though OSPF has a lower AD, the OSPF route didn't enter the routing table until I disabled RIP. It seems to be dependent on the platform and OS version. I couldn't find any public Cisco documentation about exactly how it works for iOS routers. But in any case, the whole point of this demonstration is, when configuring floating static routes or changing protocol AD values, avoid giving different route sources the same AD. The results can be unpredictable. Instead, if you want to make a router prefer routing protocol A over routing protocol B, make protocol A's AD lower. So if you want OSPF to be preferred over EIGRP, make OSPF's AD lower than 90, or make EIGRP's AD higher than 110. And to configure a floating static route, make its AD higher than the main route. So just keep that in mind. Avoid having the same AD for different protocols or sources. Now let's move on to metric. This slide is just going to be a wall of text. Bear with me, and then we'll look at some concrete examples of route selection after. AD is used to select among routes from different sources, but metric is used to select among routes from the same source. Like AD, a lower metric is preferred. So AD chooses the source, and metric chooses the best path or paths from that source. Metric values are protocol specific, so they're not comparable between different protocols. That's why we have AD. If you have an OSPF route with a metric of 10 and an EIGRP route with a much greater metric, it doesn't matter that the OSPF route has a lower metric. AD already decided the winner. If multiple routes from the same source have equal metric, the router can install them all as equal cost multipath, ECNP routes. IGPs like RIP, EIGRP, OSPF, and ISIS will install up to 4 routes by default in IPv4, or 16 in IPv6, at least on the devices I checked, and BGP installs only 1. But you can use the command maximum paths to modify it in router config mode for the specific protocol. Final point. Like AD, metric is only considered while building the routing table. Packet forwarding will then just use whatever routes were installed in the table. More on that later. So as I said, each protocol's metric values are specific to that protocol only. Each protocol calculates its metric differently, so metric values only make sense within that protocol. RIP uses a simple hop count, the number of routers in the path. EIGRP uses a composite metric that, by default, counts the bandwidth of the slowest link in the path and the delay of all links in the path. We'll cover that in the EIGRP section. As you know, OSPF uses a cost per interface, automatically calculated by dividing the reference bandwidth by the interface bandwidth. The path's metric is the sum of all link costs. ISIS is similar, but by default it uses a value of 10 on all interfaces. There is no automatic bandwidth calculation. BGP is different from the others. It uses various path attributes like the AS path, local preference, MED, and others. So it's more complex than a simple metric value. We'll learn about those attributes later in the course. Now let's look at a few examples of route selection in the control plane. Here's the first question. A router learns these 4 routes. Which route or routes will it install in its routing table? Pause the video if you want to think about it. The key here is that all 4 routes have different destination prefixes. So the router installs all 4 routes. AD and metric are only used to compare routes to the same destination prefix, the same network address, and the same prefix length. There's lots of overlap here. The /27 sits inside the /26, then the /25, then the /24. But for control plane route selection, they are different prefixes. Okay, next one. Which of these 4 routes will the router install in its routing table? Again, pause the video if you want to think about it. This time, the router learns 4 routes to 2 different prefixes. So it will select the best route to each prefix, which means these 2. The static route to the /16 beats the EIGRP route, and the OSPF route to the /24 beats the RIP route. Each route is from a different source, so AD is the decider. Okay, last one on this slide. Once again, which of these routes will the router install in its routing table? Pause the video if you want to think about it. This time, there are routes to 3 different prefixes. The 2 routes to /24 are both RIP routes, so AD is tied and the lower metric of 4 wins. The 2 /25 routes are different prefixes, so those routes are both installed. So the router ends up with these 3 routes in its routing table. Let's do a few more examples. This time you've configured these 4 static routes. Which will the router install in its routing table? Feel free to pause the video. The key here is that the first 3 routes all have the same AD. The third one specifies an AD of 1, but that's the same as the default. So all 3 are installed. The 4th route is a floating static route with an AD of 2, so it will only be selected if the other 3 are removed. On Cisco iOS, static routes have a metric of 0, so metric doesn't matter when choosing between static routes. AD is what decides. Okay, next one. Pause the video if you want to think about the answer. This time, we have 4 routes to the same prefix, all learned through OSPF. Their ADs are tied, of course, but 2 of them have a lower metric. So these 2 will be installed using ECMP. The other 2 will only enter the routing table if the 2 metric 10 routes are removed. Finally, one last example, this time using IPv6. Again, we have 4 routes. Which will the router install in its routing table? Pause the video if you want to think about it. All 4 routes have the same destination prefix, 2001 DB8/64. This time we have a connected route which has an AD of 0, so the connected route wins due to having the lowest possible AD. If that interface goes down, the static route will be used, then the EIGRP route, and then the OSPF route in order of AD. Okay, those were 6 examples of route selection in the control plane. How a router chooses the best route or routes to each prefix to build its routing table. Finally, let's look at data plane route selection, how routers forward packets. Since we covered this in the Layer 3 forwarding video at the beginning of the course, I'll just give a few points for review, and then we'll try a couple of examples. As we just covered, a router builds its routing table by selecting the best route or routes to each destination prefix using AD and metric. This is control plane route selection. When a router makes a forwarding decision to forward a packet, it selects the most specific matching route, the matching route with the longest prefix. This is data plane route selection, and AD and metric don't matter at this point. If multiple routes exist for the same prefix, the router load balances across those next hops, which is called ECMP. If no specific route matches, the router will use a default route if present, otherwise the packet is dropped. Note that in modern Cisco routers, this is done by Ceph using its forwarding table. It doesn't use the routing table itself, although the forwarding table is derived from the routing table. And that's all I have to say about packet forwarding. It's simpler than control plane route selection, since all you have to consider is the most specific matching route. But sometimes that can be tricky, especially if you're not comfortable with subnetting and identifying the address range of subnets. Let's look at a couple of examples to practice. First, using these routes here, a default route and 3 more specific OSPF routes. Let's use a few different destination IPs and think about which route will be used for each. First, if R1 receives packets destined for 192.168.10.20, which next hop will it forward those packets to? Pause the video if you want to think about it. Remember, find the most specific matching route. And that route is the one to 10.0/26, with next hop 10.0.0.2. The packet matches that route and the default route, but of course the /26 prefix length is more specific than /0. Next, what about packets destined for 192.168.10.70? Again, pause the video to think about the answer. This time, the packet's destination matches 3 routes, but it will select the /27 route to next hop 10.0.0.4 because it has the longest prefix length of those matching routes. And one more example, packets destined for .129. Pause the video if you want to think about the answer. This address matches only the default route, so it will forward the packets to next hop 192.0.2.1. Okay, let's do a few more with a new set of routes. 4 routes from different routing protocols, but don't be fooled by the different ADs and metrics. First up, which next hop will be used for packets destined for 172.16.5.35? Pause the video to think about the answer. This address matches 3 routes, the /24, /27, and /28 routes, so it selects the most specific of the 3, the /28 route. Next, what about packets destined for .50? Again, feel free to pause if you want to think about the answer. This address also matches 3 routes, the /24, /27, and /29 routes. So the /29 route is selected, and the packet is forwarded to 10.1.1.4. And one last example. This time the packet is for .63. Once again, pause the video if you want to think about it. This packet's destination matches only one route, the /24 route, so it will use nexthop 10.1.1.1. Okay, those are all of the examples we'll look at. Hopefully these were fairly easy for you to solve. Finding the most specific matching route is definitely a CCNA level skill, but it's a very important skill, even at the CCNP level, so it's worth practicing. Okay, here's a summary of the basics of route selection. I'm not going to read this slide out since most of the material in this video was review anyway. But if you're still feeling a bit fuzzy about route selection in the control and data planes, AD, metric, most specific match, etc., definitely spend some time working on these basics. And make sure to use the flashcards to memorize the default ADs of the protocols and other route sources in the chart. And that's all for this video on route selection. Just remember that AD and metric are used to build the routing table in the control plane, and then in the data plane, packets are forwarded using the most specific matching route. Thanks for watching, and I'll see you in the next video. Before we wrap up, I want to say a quick thank you to the channel members whose names you see on screen. Your monthly support helps me keep making these videos and keep this content free for everyone on YouTube. I really appreciate it. Thank you for your support. If the video was helpful and you want to support me, click the join button under the video. And please subscribe and like the video. It really helps me grow the channel and keep making these videos for you all. Thanks again.